So today I'll be discussing with you the current of electricity. So what happens is for this particular chapter, there are some things that you will need to know, like how do you calculate current, energy, and charge, and etc. But before that, let's look at what are the common kinds of electrical circuit system. Electrical circuit systems are basically diagrammatic symbols that we use, right, to actually draw an electrical circuit. So over here we have in this case it's actually a battery cell. Some textbook they'll say battery, some books they'll say cell, but generally it's roughly the same. It's just that battery sometimes they will have more than one cell. So for cells, right, you will see that the line, right, there's one line that is actually longer than the other. So the longer line represents the positive terminal of the cell, whereas the shorter line represents the negative terminal. Okay, then of course, if you have more than one cell, it's actually a range of batteries lah, in that case. For the third image, right, which has actually a circle and a cross inside here, so this represents the light bulb. The light bulb, or basically a lamp, which actually glows when electrical current is being fed into it and to display light energy. Okay, you have the switch. One thing to note is this switch, right, the circles are actually open, and at the same time this represents an open switch because this particular line is not touching to the other circular item, and this would mean that the circuit it's open, electricity cannot pass through it. You have an LDR over here, which we will discuss more in the next few chapters. We have the fuse. Now the fuse, the interesting thing between a fuse and a fixed resistor, right, is that the fuse has a single line crossing over the whole box. This is where, right, it imitates where it's like an invincible wire, where if too much current goes into it, it will actually snap and break the circuit. So that's a fuse. You have an ammeter, which is a circle with an A inside. That one is more for measuring electrical current. You have a V, which is the voltmeter. Now for voltmeter is to measure voltage or potential difference. But do take note, right, later on you'll see for drawing of circuit diagrams, right, your ammeter must be connected in a series arrangement, which we'll discuss more, and the voltmeter must be connected in a parallel arrangement. Your switch, when closed, you can see the line actually touch each other. Then of course you have a bell, you have a fixed resistor. There are two types of resistor, fixed and variable. So what's the difference is that the resistor, when we say it's fixed, right, you could see that there's no line inside, right, that would be a fuse. So this will actually showcase that there is actually indicated value for it, and you cannot change the value of the resistor. Whereas for variable resistor, it's like there will be some knobs which allows you to adjust and to actually vary it, such that you will be able to actually control the amount of resistance for it. You have a thermostat and your diode, which we will actually go through in the later part of the chapter. Next, we do see that for current, so what current is actually a rate of flow of charge past a given point in an electrical circuit, and this is usually measured in ampere. In other words, right, ampere can also be represented as coulombs over second, which is charge over time. And the formula for current is actually I equals Q over T, where I is actually the current. And this one, usually the SI unit is ampere. Q is your charge. Okay, this one is mainly your C, and then T is your time, which is usually in seconds. So that's where they have the coulombs per second kind of thing for current. But conventionally, do write ampere. So let's look at the first example. Over here, we do see that a current has 3 ampere that follows. So that will usually what I will do is I will actually indicate what kind of item it is out of this 3. So in this case, we could see that 3 ampere is actually referring to a current, and it flows in a wire connecting to terminals of a battery. Calculate the electrical charge passes through the circuit in 5 minutes. So one thing to note is, you see this is 5 minutes, but the formula requires in seconds, right? So you will need to do a conversion. So 1 minute contains 60 seconds. Of course, 1 hour equals to 60 minutes, which is equals to 60 times 60, 0.3600 seconds. Generally that's it lah. And then of course what we will do is we just put into the formula. Usually what I would advise students to do is please write the formula as a step, then you follow through. Why? Because sometimes you may, if it's all numbers, you may lose what is the purpose of this step. And at the same time, it's very clear when Q means you are calculating a charge. This will also indicate that you can put in the SI units at the end. Okay, when a total of 200 charge is being passed through an electrical circuit, the current 5 ampere is actually recorded. What was the time taken for 200 charge to actually pass through? Basically, again, you see, you write the formula and then you do the calculations. For work example 2, a conducting sphere, let's say, has a positive charge of 0.0024 charge and is supported by an insulating stand. Connected to an earth wire, becomes completely neutralized. The average current flowing is actually this amount. So now you have the charge, you have the ampere. What you want to do is you want to find time. So that's where again time equals to charge over current, you get the answer. And then in which direction does charge flow during the neutralization? Generally, this is in the chapter of static electricity, where the electrons will flow from the earth wire to the conducting or generally it will flow from the earth to the conducting sphere. So that's where electrons are being moved. Next, let's look at the flow of electrical circuit. Now there is two main things that you need to know, which is number one, the model explaining electron flow. The other one is conventional current. Both of it are moving in opposite direction. Okay, so the one in blue represents the electron flow in a circuit. So if you look at the right hand side over here, you will see that the blue one, the movement of the electron flow is from the positive terminal to the negative terminal. Okay, whereas for conventional current, it will be from the what I meant is for electron flow, it's from the negative terminal moving towards the positive terminal, whereas for the conventional current, it's actually like one in purple, where it's from the positive terminal moving to the negative terminal. So it moves in the opposite direction. So what is then electron flow? It is mainly the movement of electrons in your wires, and that will actually be responsible for carrying the electrical current. Whereas for conventional current is discovered before electrons, and therefore it tends to move from the positive charge terminal of it's a flow of the positive charge from the positive terminal to the source, which is the battery, to the negative terminal. Okay, so it's positive terminal of the source, the battery, to the negative terminal. So then the question, electron flow and conventional current, they flow in two opposite directions. Which is correct? It depends on the question, but we tend to use conventional current for our study, meaning the movement from the positive terminal to the negative terminal. Okay. Next, we look at electromotive force. So electromotive force is the work done by a source in driving a unit charge about a complete circuit. Now a lot of you may have the confusion that isn't it voltage. Now the difference is that for electromotive force, it is mainly driven by a source around a whole circuit, not part of the circuit but the whole circuit. Okay, and it's work done. So the SI unit for EMF is actually in voltage or energy, joules per coulomb, which is energy over charge. So a source of an EMF would represent that 1 joule of work is done by the source to move 1 charge around a complete circuit. And that's why your EMF is equals to work done over charge. The work done driven by the electrical energy. Okay. So next is potential difference. So for potential difference, across a component, is the work done to drive a unit charge through a component, meaning it's like part of the whole circuit. So it can also be defined as the amount of electrical energy converted to other forms when each unit of charge passes through a component, like let's say a light bulb. Okay, so one very big difference between EMF and potential difference is that one is taking into consideration the whole electrical circuit, the other is talking about the respective individual components or the things that you put into the circuit, like a resistor, a light bulb, etc. Okay, so the components can be, like I say, resistors, variable resistors, even light bulbs, and the unit for the potential difference across a circuit component is what we call voltage. Next, we look into resistance. So we have already talked about current, we have talked about voltage. So for resistance is generally the ratio of potential difference applied to the current. Meaning when we talk about ratio, we are talking about a division. Okay? And so it's generally, in simple terms, right, how difficult it is for a current, electrical current, to flow through a conducting material. So resistance equals to voltage over current, or V equals IR, for some who wants to remember it that way. So what happens is, the higher the resistance value, the greater it is, or the harder it is for the current to flow through. Whereas the lower the resistance, the easier it is for current to flow through. So how are we able to determine resistance then? Because there is no instrument to actually measure resistance technically, we can always adjust resistance. So what can happen is, we use a current, an ammeter, or a voltmeter, to actually, with these two values and the formula, to predetermine what is the whole approach towards measuring resistance. Okay, and what happens is, by adjusting the variable resistor, we usually record the ammeter reading as well as the voltmeter reading over a period of time. And what will happen next is, we actually do a plot. The gradient would represent the resistance, because assuming that this resistor is consistent throughout. Of course, by changing the amount of flow, we will be able to have an idea of how the resistance is calculated by plotting a graph of voltage against current, where the gradient is of the graph represents the resistance of the conductor. Okay. For effective resistance in a circuit, we must be very clear as to how to calculate effective resistance. Effective resistance, in other words, is actually the total resistance that is actually calculated in a particular circuit. Okay, and generally in the arrangement of a series or parallel, which we have already talked about it in your lower sec science, is that the form of calculation is very different, because in a series, the calculation of the total resistance of the circuit is just a summation. You just add all the resistance value up. Whereas in a parallel circuit, it's basically the sum of the reciprocal of the individual variation. So if, let's say, I were to give you an example, let's say in the first one is a series, where series are basically, there's only one single pathway for electrical system to pass through, whereas for parallel, you have a dividing or more than one way for electricity to pass through. You could see that for resistance in a series is basically a summation, whereas resistance in parallel is a reciprocal. And a lot of students tend to forget, right, for the 1 over RE, right, you have to re-flip it back to find RE. Okay, and one thing to note is that what we can see is, by increasing the amount of resistance in a series, the total resistance will increase. However, in resistance in parallel, when you increase more and more resistance in a parallel circuit, the overall resistance would actually decrease. So it has an opposite kind of movement. Okay. What are some things that can actually influence or affect the resistance in a conducting wire? It's like the length and the cross-sectional area, as well as the material. So when we talk about length, having a very long wire, right, it takes more, along the way you have more resistance. Why? Because it is harder for you to move. So imagine if you walk a short road versus a long road. A long road creates more friction, and therefore it will tentatively be harder to move where as compared to a shorter distance. So that's where length plays a matter. Cross-sectional area is basically the area on which basically the thickness of the wire. So having a greater surface, greater area, right, the the resistance will be smaller because there's like more place for the current to flow through. However, having a very small wire, or a smaller area, everything is so tight and cramped. So that will actually result in having greater resistance for the movement of electrical current. So type of material, different conductors can have different levels of resistivity. Now, it is not really needed for you to memorize the respective individual value of the resistivity, but it's good to know how to calculate it in terms of length and cross-sectional area. Okay, so we could see that resistance, which is the capital R, equals to resistivity P or rho times the length divided by cross-sectional area meter squared. Do take note that you have to do the respective calculations, like area. If it's a circle, it will be pi r square, and if it's a square, it's length times breadth. One thing to note is that the material, right, of the resistivity will always be constant. So like I say metal, the metal will have a designated resistivity. If I say aluminium, they have their own value. On the other hand, the length and area can always change, and that will influence the resistance. So materials with lower resistivities, they tend to be very good conductors of electricity. Next, we move on to Ohm's law. Now, this one, it is very important that you have to remember and memorize, because Ohm's law states that the current through a conductor is directly proportional to the potential difference across it if the temperature remains constant. So for ohmic conductor, it is a conductor which obeys Ohm's law. For non-ohmic conductor, it is the conductor that does not obey Ohm's law. So since voltage divided by current is constant, and that resistance equals to voltage divided by I, okay, the resistance of ohmic conductors is usually constant also if the temperature remains constant. So what we can say in this is that resistance will never change that much if and only if temperature is the same throughout. So how do we see it from a graph, right, or the characteristics from a ohmic conductor at constant temperature? We use a current against voltage graph for ohmic conductors, and we plot it through a straight line. It has to pass through the origin. Origin means 0, 0. Why? Because at the origin 0, 0, if there is no current, there is no voltage. Okay, and therefore, because it's a straight line, the resistance is constant. So the conducting wire made up of metals such as copper, iron, silver are generally the ohmic conductors, and that the constant or a very small change in temperature. Non-ohmic conductor, on the other hand, is opposite, meaning it does not always behave in a straight line, because as current increase, okay, it tends to generate more heat, and therefore increase temperature, increase resistance. So that's like for a filament. However, a semiconductor diode has a more forward direction, so when you increase the current, there is a decrease in resistance, and therefore when it has a reverse direction, there is no current flow, and therefore it will increase in resistance even greater. So comes a diode. So the diode is basically a device that allows current to flow in one direction only. It is generally made up of a semiconductor material where alternating current can be usually switched to a direct current using a diode rectifier. So this process is by which the alternating current, right, usually from the main supply, is then turned into a direct current, and therefore it functions in two different ways: forward bias or reverse bias. So what is then forward bias? This is where the diode has to be connected in a way such that it can only conduct electricity as it allows electricity to flow through. So this is forward bias. On the other hand, for a reverse bias is where the diode is connected in a way that does not allow electricity to pass through. So it's like hindering you or pushing against that flow. So that is actually a reverse bias. Half wave rectification is where it contains a single diode in the circuit to rectify the alternating current. So only the forward bias current can flow in the circuit, but the reverse one is blocked. Now this is happening in the form of alternating current because direct current is always like positive. Let's assume lah. But for alternating current, you will have both positive, negative movement with a single diode that is more forward bias. You would see that it will actually take the positive side only, while the negative one, which is the reverse side, right, is actually prevented. So there are some circuits, right, that only reach direct current, but if let's say the current source supply is an alternating current, doesn't mean that it doesn't work anymore. Instead, you just install a diode to convert it to only accept the positive side. Okay. For full wave rectification is making use of 4 diodes rather than 1 in forming a bridge. So what happens is it both puts both the forward bias current and the reverse bias current are rectified to flow in the same direction. So in a way, it's like you're flipping the negative alternating current to the top and fully converting the whole alternating current into a direct current. So this is different from just now where you only take the positive side of the current. So now you flip, it will be both sides. Okay. So this one you can pause and you can read yourself to try to make sense of it. And that's all for this particular chapter. Okay, so this is mainly to give you a brief overview of the electrical symbols, what's a diode, how to calculate resistance, how do you interpret what's Ohm's law, as well as ohmic conductor. Okay, the next one we will talk about really the calculation of current, voltage, and resistance in the series and parallel arrangement. Thank you.